Hello and welcome once again to our chemistry class. This is our fifth session, and in our previous four sessions we have studied about two units from both physical and inorganic portions. So today let us take up a unit from our organic chemistry portion, and the unit that I have selected is unit 10, and it is about haloalkanes and haloarenes. Now, for a better understanding of this unit, let us first try to remember some of the things from organic chemistry that we studied in class 11. Like, what are hydrocarbons? And what are alkanes and arenes? Or what are alkyl and aryl groups? Also, what are halogens? Hydrocarbons, as we have studied in class 11, these are the compounds containing carbon and hydrogen only. And saturated hydrocarbons, the hydrocarbons which contain only single bonds between the carbon atoms, they are called as alkanes. The aromatic hydrocarbons are called as arenes. If we remove one hydrogen each from alkanes, we get alkyls. And from the arenes, from the aromatic ring of these arenes, if we remove one hydrogen, we get this aryl group. Halogens, these are the compounds from group 17, and these include fluorine, chlorine, bromine, and iodine. So I hope you remember these things now. Keeping this in mind, let us try to now understand what are haloalkanes and haloarenes. Haloalkanes, these are the organic compounds which are represented by the general formula Rx. Here R is in alkyl group and X is a halogen, any one of these halogens. So haloalkanes, in other words, they are also named as alkyl halides, or also named as haloalkanes. So these haloalkanes can also be defined as derivatives of hydrocarbons or halogen derivatives of aliphatic hydrocarbons, in which one hydrogen atom is replaced by a halogen atom, or it may be one or more hydrogen atoms replaced by these halogen atoms. For example, if we have methane, which is a hydrocarbon, a saturated hydrocarbon, or we can call it as an alkane also. If we replace one hydrogen here by a halogen, let us say by chlorine, then we get CH3Cl. Here we get a haloalkane. This is named as chloromethane, or it is also named as methyl chloride. So by replacing one hydrogen from this hydrocarbon by a halogen, we get a haloalkane. In certain cases, more hydrogen atoms may also be replaced. Then we have the haloarenes. Haloarenes are the compounds that are represented by the general formula ARX. Once again, X stands for a halogen and AR stands for in aryl group. So these haloarenes can also be defined as halogen derivatives of aromatic hydrocarbons in which a hydrogen atom of the aryl ring, the aromatic ring, is replaced by a halogen atom. Or it may be that more hydrogen atoms can also be replaced by these halogen atoms. Now these haloalkanes and haloarenes, they constitute an important class of compounds, and their study becomes interesting and very much important because of two main reasons. First, these haloalkanes and haloarenes, they form important intermediates in organic synthesis. That means during the synthesis of many organic compounds, first these haloalkanes and haloarenes are prepared as intermediates, and from these intermediates, the required products are obtained. Now there are two reasons why they act as important intermediates in these organic synthesis reactions. The first reason is because the haloalkanes as well as haloarenes can be very easily prepared. They can be very easily prepared. And the second reason is because they undergo reaction very easily. So they can be easily prepared to form the intermediates, and the intermediates will easily undergo reactions to form the products. It is for these reasons that these haloalkanes and haloarenes form very important intermediates in organic synthesis. The other reason why the study of these haloalkanes and haloarenes is important is because these compounds, they find wide applications in industry, in medicine, in surgery, as well as in their use as insecticides and pesticides. For example, chloroquine, a derivative of these haloalkanes, it is used for the treatment of malaria. And hydroxychloroquine, which is a derivative of chloroquine, is now under study as a potent medicine or drug for the treatment of this COVID-19 disease. Not only that, some haloalkanes or derivatives of haloalkanes like DDT, dichlorodiethyl trichloroethane, or BHC, benzene hexachloride, these are used as insecticides and pesticides. There are still other compounds of this family like halotane, which is used as an anesthetic. Or still there are some which are used in surgery or in other industries. However, there is a growing concern about the use of these haloalkanes and haloarenes because they produce compounds like chlorine, that means the halogens like chlorine and bromine, which are harmful for the atmosphere. For example, global warming or depletion of ozone layer, all these are caused by compounds like chlorofluorocarbons, which comes under this haloalkanes and haloarenes. So it is very important for us to study this properly and understand them so that we can modify them or we can synthesize alternative compounds to replace this which are already in use and which are harmful for us and for the environment also. Now, having understood this, let us go into how these haloalkanes and haloarenes can be classified. What are the different types of haloalkanes and haloarenes? Now this classification of haloalkanes and haloarenes is done based on two things. The first one, it is based on the number of halogen atoms. Based on the number of halogen atoms. So if we have one halogen atom in the compound, we call it as a monohalo compound. If there are two, we call it as a dihalo compound. If there are three, trihalo compound. Or if there are more, we call them as polyhalo compounds. For example, if we have CH3Cl, this is chloromethane. Here we have only one halogen atom. So this is a monohalo compound. Likewise, if we have CH2Cl2, this has two halogen atoms, so this will be a dihalo compound. If there are three, it will be a trihalo compound. If there are four, a tetrahalo compound, and so on. So usually, those which have two or more halogen atoms, they are called as polyhalo compounds. So based on the number of halogen atoms, we have monohalo compounds. Then we have dihalo compounds. Then we have trihalo compounds or tetrahalo compounds, and so on. Now, the monohalo compounds, those which contain only one halogen atom, they can be further classified into two main types. We have sp3CX bonded compounds, and we have sp2CX bonded compounds. In this, the halogen atom is bonded to a sp3 hybridized carbon atom, whereas in this one, the halogen atom is bonded to a sp2 hybridized carbon atom. Now, under this sp3 CX bonded compounds, there are three different types again. So we have the alkyl halides, in which the halogen atom, it is bonded to a carbon atom, which is again bonded to other carbon atoms by single bonds only. That means the halogen atom is bonded to a carbon of an alkyl group. These are called as alkyl halides. Then the next one, we have allyl halides or allylic halides. In this, the halogen atom, it is bonded to a carbon atom which is sp3 hybridized, but this carbon is bonded to another carbon which is sp2 hybridized. That means the next carbon atom is bonded to another carbon by a double bond. This will be called as allylic halides. And the third type, we have benzylic halides. In this, the carbon atom, the halogen atom, it is bonded to a carbon atom which is again bonded to an aromatic ring. It may be the benzene ring or any aromatic ring. So usually, as the name suggests, benzylic halides. So usually this aromatic ring will be the benzene ring, to which the carbon to which halogen atom is attached is bonded. So these are the three different types of halides or halo compounds that come under this sp3-CX bonded compounds. Then the next one, in this one, the halogen atom is bonded to a sp2 hybridized carbon atom. Under this also we have two types. We have the vinylic halides. In vinylic halides, the halogen atom, it is bonded to a carbon atom which is bonded to another carbon atom by a double bond. That means this carbon atom to which the halogen is attached, it is sp2 hybridized. Then finally, we have aryl halides. In this one, the halogen atom is bonded to a carbon atom of the aryl ring. So this carbon actually belongs to the benzene ring or any aromatic ring. So these aryl halides, they are also called as haloarenes. Now, keeping in mind these different types of haloalkanes and haloarenes, let us see how they are named, how these haloalkanes and haloarenes are named. Now, all the rules of naming that we have seen in class 11 for naming organic compounds, whatever rules we followed, like the longest chain rule or the lowest locant rule, all of those rules will be followed here also. However, there are some important things to keep in mind while naming these haloalkanes and haloarenes. The first thing is that while naming the haloalkanes, if we are using common name, the alkyl group will be named first, and then the halogen will be named last. So if we have CH3Cl, if we are giving the common name for this compound, this will be named as methyl chloride. So in common system, the alkyl is named first and then the halogen later. But if we are using IUPAC nomenclature, the halogen will be named first and then the alkane. So this will be named as chloromethane. Likewise, if we have another compound, C2H5Br, if we give the common name, then this will be named as ethyl bromide. But if we are giving the IUPAC name, this will be named as bromoethane. So once again, while naming these haloalkanes, if we are giving the common names, the alkyl group will be named first, then will be followed by the name of the halogen. But under IUPAC nomenclature, the halogen atom will be named first, and then the name of the alkene will follow. Now, if we have monosubstituted derivatives of benzene, that means compounds like C6H5Cl, suppose, which can be represented like this. monosubstituted means one hydrogen of the ring has been replaced by a halogen. If we have monosubstituted derivatives of benzene like this compound, then common name as well as IUPAC name will be the same. So this will be named as chlorobenzene only, under common name as well as under IUPAC name. That means for this type of compounds, the halogen is named first and then the ring is named later on. Now if we have di-halosubstituted compounds, if there are two halogen atoms in the ring, suppose two hydrogen atoms have been substituted by chlorine atoms in the ring, we have a dichloro compound or a di-halosubstituted compound. In this type of compounds, under common name, under common system of nomenclature, we use the prefixes O2, para, or meta to indicate the position of the second halogen atom. So if we have the compound like this, these two positions which are near to this halogen, these are called as ortho positions. The next two positions, they are called as meta positions, and this position which is just opposite to this position will be called as para positions. So we have two ortho positions, two meta positions, and one para position. So under common name, this second halogen atom, it is at meta position. This is the ortho position, this is the meta position. So this can be named as meta dichlorobenzene. But under IUPAC nomenclature, we don't use these prefixes. We use numerals instead. So if this is position 1, this is 2, and this is 3, then this will be named as 1, 3, because the halogen atoms are at carbon 1 and carbon 3. This will be named as 1, 3 dichlorobenzene. So once again, for di-halosubstituted compounds of benzene, under the common system, we use the prefixes ortho, para, or meta. But for the IUPAC nomenclature, we will use these numerals. So if we have this halogen here instead of here, then under common system, this will be named as O2 dichlorobenzene. And under IUPAC name, it will be named as 1,2 dichlorobenzene. So these are some important points to keep in mind while naming these haloalkanes and haloarenes. Now let us see some of the methods by which we can prepare these haloalkanes and haloarenes. There are many methods actually that can be used for preparation of these haloalkanes and haloarenes. But we will be able to see only some of them. So the first one, first let us see the preparation of haloalkanes. The first method is from alcohols. Haloalkanes can be obtained from alcohols by treating the alcohols with any of the halogen acids or with some phosphorus halides or thionyl chloride. Any of these reactions can be used to react with alcohol to obtain haloalkanes. For example, if we have ethanol in alcohol, we treat this with a halogen acid like HCl. What happens is this OH group of the alcohol is replaced by the halogen from the acid. So we get C2H5, and in place of OH now Cl comes. Therefore, ethanol gets converted to chloroethane. Water will be given out as a byproduct. Instead of HCl, we can use PCl5, phosphorus pentachloride. We can use PCl3, phosphorus trichloride. We can use thionyl chloride also. All of this can be used to convert these alcohols to haloalkanes. But among all of these, thionyl chloride is usually preferred because when we use thionyl chloride to convert alcohols to haloalkanes, two byproducts obtained are in the form of gases which can be easily removed. Let us see how the reaction goes. Suppose once again we have ethanol. We treat it with thionyl chloride. We get chloroethane, and then sulfur dioxide, and then HCl gas. OH group here is replaced by one halogen from here, so we get C2H5Cl, chloroethane, a haloalkane. Then we have SO2, a gas, and then HCl, which is also a gas. The second method for preparation of haloalkanes is from hydrocarbons. Now we can use alkanes as well as alkenes for preparation of these haloalkanes. First, let us see how they can be prepared from alkanes. Alkanes, they can be easily halogenated in the presence of UV light or in the presence of heat to obtain these haloalkanes. So if we have an alkane CH4 methane, we treat this with a halogen, let us say chlorine, in the presence of UV light or in the presence of heat. We will get CH3Cl, and one molecule of HCl will be given out. That means in the alkane, one hydrogen atom is substituted by a halogen. So here we get a mono-halo compound. This reaction can proceed further until all the hydrogen atoms are replaced by halogen atoms. So another HCl molecule will be lost, then we will get CH2Cl2. Then this can go further and form CHCl3. Then finally the last hydrogen can also be replaced to give CCl4. So in the first step we get a mono-substituted, a mono-halo compound, then a di-halo compound, then we have a tri-halo compound and a tetra-halo compound. So actually in this method, we get a mixture of mono, di, as well as poly-halo compounds. And therefore, this cannot be used if we want only one product. If we require a mixture of these products, we can use this process. But if we require only one particular product, we cannot use this because we usually get a mixture of these products. The second method is from alkenes. Now, alkenes can be treated with halogen acids when the halogen acid gets added to the alkane to give this haloalkanes. So if we have ethene, which is an alkane, we treat it with a halogen acid like HCl, then addition takes place across the double bond. Now this molecule breaks up into these two parts, a positive part and a negative part. One goes to the first carbon, the other goes to the second carbon. The addition will take place across the double bond. Now if we have symmetrical alkenes like this, similar groups on both sides of the double bond, then the product form will be similar no matter what. Suppose hydrogen comes here, we get CH3, and then the halogen comes here, we will get CH2Cl. If the hydrogen comes here and the halogen comes here, the product would be CH2Cl and CH3. These two are actually the same. They are similar. So we get only one type of product when we add these halogen acids to symmetrical alkenes. But if we have unsymmetrical alkenes, then the addition takes place in such a way that the negative part of this molecule which is added goes to the carbon with less number of hydrogen. This is in accordance with Markovnikov's rule, which we studied in class 11 also. So the negative part of this molecule to be added goes to the carbon with less number of hydrogens. As I said, addition takes place across the double bond. Out of these two carbons, this has less number of hydrogens. So the halogen atom comes here. That means the negative part comes here. The positive part goes to the carbon with more number of hydrogens. So the product formed will be CH3CH. Cl will come here, and then the positive part, hydrogen, will come here. So we get this. So this will be the major product formed. The minor product may also be obtained, and it will be CH3, CH2, CH2Cl. Both of these two products may be formed, but the major product will be this one, the one in which the halogen, the negative part, has added to the carbon with less number of hydrogen atoms according to Markovnikov's rule. So these are some of the methods by which we can prepare haloalkanes and haloarenes. Actually, we have seen only the preparation of haloalkanes today. In the next class, we will see some methods for preparation of these haloarenes also. That is all for today. Thank you.